everyone. Hope everyone's doing as well as I am. And I'm not doing too good, so I guess I don't want that for anybody, really. Maybe it's the other way around. I hope you're not doing as bad as I am. Yeah. Couple things. First one is my article on orthogonality and fields, electromagnetic fields, why they're orthogonal, why they're perpendicular to each other, was released. I won on appeal with Quora, and so they released it. And essentially, what I did was remove the reference to Facebook. Apparently, they don't like people. I guess they consider it spam if you go out there and send people to your own site or to some other site that you're sponsoring or whatever. So once I removed that, they authorized the article, and that was the article on fields. Here it is. Why electric and magnetic fields? Why are electric and magnetic fields perpendicular in an electromagnetic wave? And as you can see there, I put in the article, what is it here? It says, the word field belongs exclusively to religion. Now that's a good way to start a fight. Right? Yeah, okay. And, and that there are no such things as fields, and the word field means region in mathematical physics. That's all it means. And I went through and discussed what this guy, Sean Carroll, essentially said. I use his words, and his words are, field is no doubt a region, okay? So anyways, they released it. If you want to read it, well, you got a chance there. Now it's back in line. The other one is I need to remind you that once more, and I'll remind you every so often, that we have a conference on the 10th of November in Buenos Aires, Argentina. And that's the 6th Rational Physics Conference. It's hosted by David Robinson and myself. He proposed it, I accepted, and we're going to carry it out. So you are all invited. If you do want to submit a paper, you've got a month to go. It's on the 15th of September. We might extend that to the 30th of September. You submit it to the Rational Scientific Method in Facebook, or you can take it to the 6th Rational Physics Conference, also on Facebook. Okay, so you can submit it there. You can also bring it on the day that if you show up in Buenos Aires. Of course, we're going to allow it, but it won't be peer reviewed except post facto, okay, after the fact. And the other thing I want to remind you is we have the fourth video of the real physics, and it's on gravity. So if you haven't watched it yet, go ahead and watch it. Give me some feedback. It's not public yet. It's only for the rational physics folk, people who are tuned in through Patreon. Okay, and so go ahead and watch it and tell me what you think. If you've got any modifications to make that can be relatively easily done, then we'll do it. Okay. Okay, so what's the story today? The story today is that we were working on the Ptolemaic system that quantum mechanics has. So what is a Ptolemaic system? Well, it comes from Ptolemy 2,000 years ago, and he created this, more or less, all these epicycles and weird ways of moving around the sun. And in fact, it wasn't around the sun, sorry, it was around the earth. So he had everything moving around the earth. And he wasn't the only one, by the way. He just put in the Almagest, but it was very popular in those days. All the Greeks believed in this. Most people really thought that it was the Earth that was at the center of the universe, because of course we're not moving, right? I don't see myself moving or the ground underneath my feet. So it was everything else that was moving around us. We were the center of the universe, and so they created this cumbersome, incongruous system. And why do I bring that up? Because quantum mechanics is a a Ptolymaic system.
I think a better way to call it is kind of like patchwork. Where they use this to explain that, this to explain that, this to explain that. It's not like a one theory fits all. It's patchwork.
Okay.
We're gonna use this to explain that. We're gonna use this to explain that. We're gonna use
ad hoc.
ad hoc patchwork. General relativity for gravity. We're gonna use quantum for particles. This for that.
Exactly. And here's the what they ended up after 2,000 years. This is where we're at. We're with 17 particles, and we have 6 quarks. The up, down, charm, strange, top, and bottom. Those are the violet ones on the upper left. And then you have next to them the leptons. Those are the green ones. At the bottom left, electron, muon, tau, and then the neutrinos, electron, muon, and tau neutrinos, right? They interact poorly with matter. That means that they've never seen or detected them. They just know they're there because they need them in an equation. And then they have also the gauge bosons. I call them the bozos. I don't know, I like that name better than bosons. And those are the ones on the right-hand side, the pink or orange ones there, and together with the yellow Higgs. Higgs is new, and that's a scalar boson. That's why it's separate from the other 4. Okay, so far we have 17 particles, and we went over them a little bit yesterday, right? The strong force, the weak force, the big problem there is that you can't produce attraction, especially with a strong force. See, the weak force is easy. It's an expulsionary type of force. It pushes things out. Same with the photon. It's outwards. The big problem comes with the graviton, which is not in there, as you can see, and with the gluon.
What are the weak and strong forces?
They push material out of the atom. So it's so you're talking about the photon works between atoms, whereas what they're looking at is inside the atom, like what do they do inside the nucleus, and that's where they get into the weak and strong forces.
So we have 2 forces within an atom holding it together? Or?
And 2 outside.
Okay.
The 2 outside are gravity and the photon, the electromagnetic force. The 2 inside the atom, especially inside the nucleus, that's specific. Inside the nucleus, that's the strong and the weak. They had to create. See, what they did was break open the atom, or so they think, and they say, "What's in there?" And they say, "Oh, we found more particles." What particles? Well, we have the carrier of the strong force, and we have the carrier of the weak force. The weak force is the outward force, the one that pushes things out, and the strong force keeps the nucleus together, and we'll call that the gluon.
So it's the push and pull within an atom.
You got it. But the problem is the pull part. And they have the problem with the pull part with a graviton. You know, they can't produce
gluon. Gluons.
No, that's inside the atom. I'm sorry. We have 2. The graviton is outside the atom, and the gluon inside the atom. Both are pull forces, and they can't explain it with particles.
Yeah.
Okay, and so the graviton is not even part of the standard model. It's a hypothetical particle. That's why it's not a proven particle. That's why it's not on the chart. You don't see it there. See, there's the little g. That's the gluon. I guess they would put a big G for the graviton, right?
Or
and the gluon
finds it.
Yeah.
If Jim finds
Joe,
it,
that's a J. That's a J.
It's the Jim on.
No, they'll never find the graviton, so don't hold your breath. But the gluon, yeah, it's proven. You can see it's there. It's been proven.
And the gluon is the strong force within the atom
that holds the quarks together. 3 quarks inside the neutron, the 3 quarks inside the proton, and holds them together. Okay, and those are the gauge bosons. The Higgs being the scalar boson among us. Scalar means it's just a quantity without a unit, I guess. Anyways, these are
the only 17 elementary particles.
Well, they're not even elementary.
New ones,
the problem is that these
they come
guys
up with the mesons and the
and we went over that a little bit yesterday. You know, we have the mesons, the what were the other ones? The fermions, the
That's why these aren't really. This is actually incorrect. It's not standard model of elementary particles. It's standard model of particle categorizations. Because these are just how they categorize. There's many bottom things. There's many muons, many electrons, many types of each of these.
And
so these are more like branches that branch off into many, like 2 or 3 smaller ones.
And
that's why it's kind of tricky to call them elementary, because it's really classifications.
Yeah, and let's look at a visual image of what Hans just said. Here's what these people. Here's where they get all this stuff. You know, they go into the chamber. Okay, I'll move here aside a little bit. And they go into the chamber and they they smash particles, or so they think, and they get these squiggly lines. And so what they try to do is they give names to these things. Okay, so they call one Joey, the other one Johnny, the other one Peter, Tommy, and so on. And they say, well, see, this one goes faster than the other one, this line, because these things are supposed to be traces. You're supposed to be looking at traces. It's a picture of a movie. Okay, keep that in mind. It's a picture of a movie. Okay, all these are traces, supposedly. That's how they see it. And they say, look, this one has so much mass, this one has so much speed, I need so much energy to create this one. And that's how they categorize these things. They give names to these things. That's how they came up with this particle model, especially at the subatomic level. They're looking at things that are supposedly smaller than the hydrogen atom. Okay, they're looking at the components of the atom here. And so this is the image from where they get all this stuff, and so they name all these things, all these supposed particles
itineraries.
Supposedly this is the debris from when the hand grenade explodes.
Looks like fireworks.
Yeah, that's more or less what it is. Collision supposedly, and particles. This is the debris from the explosion. And whatever squiggly line you see there, they just categorize it with mass, speed, energy, and other parameters.
This is the Large Hadron,
spin.
The Large Hadron Collider?
Well, all of them. SLAC, Fermi Lab, Jefferson Labs, all of them.
What do they call that? Particle smasher?
They call them particle accelerators.
Particle accelerators.
Or just accelerators. We used to do particle accelerations. We called them implanters because we were implanting species, and we didn't work at the subatomic level. We worked at the ion and higher level. In other words, we ionized atoms, and we accelerated them along the beamline. Not at these great energies, not at these great speeds. We just needed to put them into wafers to give them electrical characteristics. Okay, so but the concept is the same. Or in other words, the machine works in the same way, pretty much as what CERN and all these other Fermi Lab and so on do. You accelerate particles. That's what it is. You do it with magnets. Once you ionize an atom, supposedly it's positively or negatively charged,
you make the atom or particle
amenable,
movable with magnets.
Yeah, it's amenable to being moved with magnets.
You change it in a way that it can now be moved with magnets, and then with magnets you can
Correct.
Do everything you want.
And that's what they do here. Okay, they accelerate particles. Okay, and so what's the deal with this? Well, we have the problem that we have more categories here. And these are a series of particles I haven't mentioned yesterday, but we're going to go through them. I like the first one, the onium, because that's named in honor of my son. He goes by Ans, and also he's known as Onion. And so this is the onium.
It's not an O, it's an A.
Yeah, but this is an onium.
My cousin used to call me Onion.
Okay, and this one is a bound state of a particle, and it's antiparticle.
What does that mean? A bound state? I thought that was the meson, the one that was a quark and an antiquark.
Yeah, but this is a different one. This is a particle. It's an antiparticle. This is a general category, so then it belongs to the onium category, right? Then we have the positronium. We mentioned that one yesterday, and that's an onium, which consists of an electron and a positron bound together. Okay, so they dance around, and you have an electron and a positron. Then we have the I can't even pronounce this, muonium, right? Muonium, and that's an exotic atom made up of an anti-muon and an electron.
I like the exotic.
Yeah, but look at this. They've modified the atom. See, the atom used to be very simple. It used to be just a proton and an electron. They say, no, now we have an anti-muon and an electron orbiting the atom. Now we have anti-muons. Did you know about that? And so it says, what is an exotic atom? It's an otherwise normal atom in which one or more subatomic particles have been replaced by other particles of the same charge. For example, electrons may be replaced by other negatively charged particles such as muons, muonic atoms, or pions, pionic atoms. So now we have more categories in the not only in the standard model, because the 17 particles are subdivided all these different categories, but we have it also in the periodic table. Now, when you go to a periodic table, you have to say, well, is that a muonic atom or is that a pionic atom? I mean, has it blended with a muon or a pion? And we replace the electron now with a muon, which weighs more, by the way. So does the pion, by the way. Electron is one of the least massive particles of this whole group.
Oh, because it only has mass when it moves or something weird like that.
Yeah, on top of well, they have the rest mass and then they have the relativistic mass. They blended relativity with this, so it's gotten very, very complex.
But that's the question. Like, do they find it easier to talk among themselves with this language? Does this simplify it even for them?
No. Clearly, this is not simplified. It gets more complicated day by day by day. And the complication is good for them because it's job security. As long as you got more complexity and you have more questions, like you said the other day, as long as you have more questions, hey, we got something to do.
The next one's even funnier.
Yeah, the true muonium.
Muonium or the muononium. Muononium.
Yeah, theoretical predicted, it's a predicted one, right? Theoretically predicted exotic atom made up of an anti-muon and a muon. So now we have an atom that no longer has electrons. Now it's got muons and anti-muons in it. And that's the true muonium.
What's
the other one is the false one, I guess.
Why do they keep using the word exotic? What do they mean?
Well, because they're saying it's not your standard atom. It's not your middle-of-the-road atom, right? Then we have the pionium. That's a pion, pionium. The pion, it's a bound state of two oppositely charged pions. Okay? And then we have the protonium, also known as the antiprotonic hydrogen. A type of exotic atom in which a proton and an antiproton orbit each other.
What's an antiproton? I thought an antiproton was an electron.
Yeah, and they just go into so many categories that you would,
Can you just put the word anti before anything?
Yeah. They have anti-color, anti-flavor. For everything that they invent an anti.
Because they say it has to. Because they have to find a way to remove it from the equation in case they need to.
No, I don't think. I think it's got to do with the fact that they suspect that for every particle there's an anti-particle. For every property there's an anti-property.
No, but I think it really comes from math, where if you want to balance out the equation, you need to put a negative whatever on the other side. So it's like if they need to get rid of
to balance
color,
it out, you mean to balance it out.
They need to get rid of the color to make the
I don't think that's true. I don't think that's true because if they take that negative proton, and they put it on the other side, it becomes a positive proton. So and you should be able to do that mathematically. Take things from one side of the equal sign, put it on the other side.
Balancing both sides, but in the function in the function itself, like just on the right side, if you need to get rid of a certain factor. You just put a negative whatever, like minus itself, and then you get rid of it that way. Maybe
I'm not sure that's what the case is. I think it's got to do more with the fact that they have anti-properties, anti-particle. It's got to do with anti-properties. They suspect that because they've seen it constantly ever since Carl Anderson found the positron, which is the opposite of an electron. It's a positive electron, essentially, and that's the antiparticle of the electron. Ever since he found that, what was it, 1936, I think it was? Ever since he found that, well, from then on, it's always become, an anti whatever. You got a proton, you got an anti-proton, electron, anti-electron, and so on. And I think it's got to do with the fact that they suspect of this duality in nature. Besides, you have matter and antimatter, and they had to produce that because that helps them also visualize a little bit of the origin of the universe. And they say, well, there was antimatter and matter, and if they come together, they annihilate themselves and become nothing. I guess a 1 minus a 1 kind of thing. It becomes a 0, positive energy, positive mass, negative mass, and so on down the line. And so then they always have the question is, why was there more matter than antimatter, at least in this side of the universe, because we are all made of matter, and the antimatter supposedly is on the other side of the universe. So they have all these weird theories to explain all these things. They all got to do with properties. But we're not done yet. Those were the particles. Now we come with some of the properties. Here we have the strange particles. These are the kaonic hydrogen, an exotic atom consisting of a negatively charged kaon orbiting a proton. We no longer have electrons. Forget about the electrons. That's old stuff. That's 19th century, 18th century maybe. The electrons are the done deal. That's boring now. Now we have to have charged kaons orbiting a proton.
The kaon. Any of a group of 4 mesons distinguished by a quantum number called strangeness.
And strangeness is a property of particles expressed as a quantum number for describing decay of particles in strong and electromagnetic interactions which occur in a short period of time.
What does that mean?
We don't know.
I couldn't even listen to that anymore.
Yeah, I mean,
my brain literally turned off.
Now you know what a particle physicist does, a particle mathematician. And then we have one of these is the strange quark, or a quark, or S quark, right? The third lightest of all quarks. We have the heavier, the medium, and this is the, you have the Goldilocks and so on. Well, this is the mama bear. This is the third lightest of all quarks. Strange quarks are found in subatomic particles called hadrons. Example of hadrons containing strange quarks include kaons, strange D mesons, sigma baryons, and other strange particles. You better believe they're strange. They're pretty strange and weird, and they have all these subcategories. You're no longer talking about mesons. Now you're talking about the D mesons, and then you're talking about the strange D mesons, and where is all this leading to? This is certainly doesn't simplify our path towards the grand unified theory, the gut. Well, yeah, this seems to take us way far away from William of Ockham.
But they just go, well, the universe is complicated.
Yeah, but is it complicated, or is this the Ptolemaic system?
Apparently, it is complicated, or else they wouldn't have made the smartest people.
Ptolemy thought the same thing. He said it's a very complex system. We have the moon and we have Mars, and Mars goes backwards in the sky. How does it do that?
If you have the wrong theory,
and they only had 5 planets.
If you have the wrong base theory, everything that you build on that becomes more and more complicated to try to patchwork, fill in all the holes of the theory. If you have a theory that doesn't blanket, it doesn't fit perfectly, and you're trying to smash that puzzle piece into the puzzle.
Yeah, but it's like you're forcefully doing that.
It's like you're trying to force it at all costs. Like, oh man, we need to plug this hole, make the kaon. We have to plug this hole.
But isn't that ad hoc? It's.
Well, but you don't know it's ad hoc until you have a better theory. That's the problem.
But
until you have a better theory, it is by definition the best thing we have. So that is how the world works.
I have a problem with that, because if these guys don't have a common sense to know that they're really getting farther and farther away from simplicity,
or the universe is complicated,
and all they're doing is they should see the parallel with Ptolemy. They should see it. Ptolemy only had 5 particles. He had 5 planets. That's it. These guys are already up to 17. They have all these subcategories. They got more than 200 categories. You could call them more than particles because they're not even particles. Corpuscles. They're not corpuscles.
Well,
they're wave functions and equations. That's all they are.
They're categories until we find the elementary particle.
But they never will, because what they're doing is just splitting up
No,
into different angles. See, if they were all on the same path, you would say, okay, we're going to get to the. They're converging upon one particle. No, here they're breaking up into more and more particles, not converging upon one particle, which is what quantum should predict. Because if there's a single particle that makes up everything in the universe, let's get to it. And these guys are getting farther and farther away from that.
We're getting further and further away from the number one. We have
exactly.
That's what I'm saying. They're all categories because as soon as you cut it into two, it is a category of those two.
Yeah,
and as soon as you cut that next one, that is a category of the next two.
Right, it doesn't converge, it breaks up.
That's what I was talking about when they called them 17 elementary particles. They're really particle classifications for subparticles and sub-subparticles and quasi-sub-quasi-sub-strange particles.
Well, talking about quasi, we have the quasi-particles or the quasi.
Oh, I thought those were the quasi-particles.
No, we haven't gotten to those. Now we're going to get into
those the weird ones.
No, those are not the weird. Now we're going to get into the really strange, weird particles.
We already had the strange ones.
Yeah, this is stranger than
these
strange.
These are the weird ones.
Yeah, those are the strange. These are the weird ones. And I call them the Quasimodo. Quasi.
It comes from the German quasi.
Yeah, and you've heard of Quasimodo. Here's Quasimodo. Look, you've seen this guy, right? And Quasimodo, he's a very famous guy. He worked at Notre Dame.
He worked there, right? Part-time. He was a part-time.
And he's the guy who saves the girl. He's the hero because he saves her from the guillotine or from being hanged. And he shows it to the crowd, great acting by Charles Lawton there. He just mans the bells, and since he's deaf, he can bang them as hard as he wants. He picks up the girl and runs off with her, and they can't kill her. And then he defends her from the tower. So he's a Quasimodo, right? And that's essentially what these guys have. They have quasi or quasi-particles. And here's what a quasi or quasi-particle is. It's a they're also known as collective excitations. In other words, this is not a particle. They're looking at some kind of vibration and calling that a not quite particle. You see a vibration, that's a not quite particle.
So it's not enough to make it a particle.
But it turns out that they're all quasi-particles because they're all wave functions.
Yeah, that's what I was going to say.
They're all so I don't know what
behaviors. They're all traces or verbs.
They're verbs without a noun. They're verbs they're all excitations. They're verbs without a noun. And here but all of these are emergent phenomena. That means emergent means that it comes through a system, builds up through a system.
What do you mean?
The vibrations all together build up a system. That's called an emergent property. Okay, and that's different than just seeing a single vibration. Here is several vibrations coming into and forming a particle, a quasi-particle, a particle that's in the process of becoming from vibrations. So a verb becoming noun.
It's enough verbs happening in the same location that you could almost call it a noun.
Yeah, that occur when a microscopically complicated system, believe me, such as a solid behaves as if it contained different weakly interacting particles in free space. And, I thought I'd look up to see, how many quasars do we have in this world. And here's a list. Here's the half the list. You've got the bipolaron, the bogolinbon.
What?
Yeah, so
Did you put up the list?
I want you to memorize all these by the test that we're going to have at the end of this. The bogolinbon, the configuron, the dislon. See, now you know what all these guys are doing. Here's the droppleton.
What the heck?
the exciton, the fracton, the fracton,
You know what
subdimensional particle, the holon,
You know
the
what-
leviton, the magnon. Yeah, what?
You know what this sounds like? It sounds like the new genders that are being made up.
Yeah.
By these
Categorizations.
it's where they're just kind of categorizing more and more. Like it's like they're breaking their head to see how many are feasible. How many categories can it? How many different ways can we put the? If we have the electron here, here, and here, we have 3 different ones. So they just go down the list of all the different positions and orientations that every single excitation or thing that they notice could even be, and they give each and every one its own A, B, C, D, E, F, G.
Yeah, because all these particles, you can see on the right-hand side it says the underlying particles. But none of these are particles because in the end, all these so-called particles are just wave functions. So what do we have? We have wave functions, a whole bunch of wave functions. There is an emergent property, which they call a bipolaron, for example. Or here's the second part of that list, just in case, just so you missed it. Here's the phason and the phonaton and the phonon and the plasmaron and the plasmon, polaron, polariton, and the roton. You know you should memorize all these things because these are important for your life. You know.
Did I read that right? There was a one that started with an F that said subdimensional particle.
Let's see, F. Where is it? Bound state, lack of electron.
In the parentheses, subdimensional particle.
I like this one. Lack of electron in a valence band. So okay, where you saw some? Oh, coherent excitation.
Fracton.
Oh, where is it? The fracton,
Fracton
a collective
in
quantized vibration.
But not that one. The one under it. In the
oh,
name of
an
it.
emergent quasi.
No, but not the signification. The quasi-particle itself has subdimensional particle.
Oh, subdimensional. Oh man.
That?
Oh man. It's a particle.
It didn't quite make it to 3. It's a 2. Right?
No, it didn't make it to 0.
Oh, true.
It's a negative dimension. Yeah, I mean, what is all this? Is this science? Is this what we call science? You know, this really makes you think about, you know, what these people are doing, what you're supporting with your tax dollars and that kind of thing. This is what these people do all day. They just create all these emergent properties, emergent particles, quasi-particles, out of particles which are not really particles, they're wave functions. They're vibrations that turn into, you know, collectively into a quasi-particle. What is it?
Okay,
what has this got to do with anything?
But step by step, what are they doing? What do they do in the lab? What do they do from there?
Well, again, they smash, or so they think. They're smashing. They accelerate what they think they're accelerating particles. Okay. And there's no acceleration. Essentially, everything is standing still. What they're doing is vibrating, you know, the threads and the atoms, the serpentines specifically. That's what they're doing along the beamline. But that's the rope model of what they're doing.
What do they think?
Let's forget about that for a second. What they think they're doing is they're accelerating particles, discrete particles. They think sometimes that they're
What do you mean by particles, not atoms?
No. We're talking about hadrons. Remember, it's a large hadron collider. You say, what's a hadron? Hadron is either a neutron or a proton.
So they just take the proton out.
Correct. They remove the electron or the electrons because I don't know how they do it with the heavier elements, but I think they just ionize. In other words, they think they're just removing one I don't think you can remove all the electrons from gold.
Yeah.
Gold has 84? I think gold has 84 protons, 84 electrons, and I don't know how many neutrons. So I don't think you can remove all the electrons. So they remove 1 or 2 maybe.
Is gold what they use?
Yeah, they accelerate gold ions, they smash them.
It has to be fancy. It can't just be like lead or something. It had to be gold.
Well, they do it with different chemical elements. They create a species, they accelerate it, they smash, they think they First they think they're accelerating only one atom or one ion. And we have a question there, but okay, let's assume that's true. So they accelerate one atom, one ion in gold ion in one direction, the other one in the other direction. So they go, in opposite direction from the top, one clockwise, the other one counterclockwise. And finally they put the beam there, again, beam.
They crash. Let's just say they crash.
How can you have a beam of one particle? Okay, but
Because
they do.
It
So
leaves a trace.
yeah. And so they smash them, as they think they do. They are able to, with their computer programs, they are able to simulate or image that there are these squiggly lines coming out of there. They say those are traces. They take a snapshot of the trace, as we saw a minute ago. Let's see if I can find it here. Where was it? Do I have it too? I get it somewhere, but article. I can't find it now. Yeah, anyways, the point is that they smash them, they see these squiggly lines, and they give them names. And then they find other properties, like emergent properties. They notice something over here, and they say, what do we call this one? And they come up with all these quasi names.
That one. So they see something's about to happen, or the signal was too weak to give it a full one?
A property emerges from the system. So they have many vibrations in there, and they say, what are we going to call this cluster? This cluster of vibrations that's apparently, like if you look at it from a bird's eye,
it seems to make a pattern.
It seems like a single entity, and that's what they'll say. Oh, we'll call this one a quasi whatever, quasi Johnny, quasi Peter, whatever. So they come up with all these names. And it's, again, what does all this have to do with science or with physics? Or it no longer is science. It's no longer physics. They're not explaining anything. They're just using equations and these visual images, these images that they manufacture, because it's not a photograph, okay? And they're images of what they think are traces. So they have images, photographs of movies. You have a movie of a particle moving, they take a snapshot of the whole thing. How do you do that? I don't know. So there's a lot involved here, and so what does all this have to do with science? What does CERN, what does Fermilab have to do with science anymore? These are white elephants. These are people out there, pushing the pencil and saying, I hope nobody notices that I'm not doing anything. So they create all these names. Well, you work on the pion, you work on the muon, and so these guys are working on these different categories. Oh, I'm a particle physicist,
and he's smart.
And everybody's just, he works at Fermi. He's got a PhD.
When you were reading those out, I didn't know what you were talking about. So, and if you have,
because you're not smart enough.
And if you're the one on the stage and you have all the medals, and I'm looking at you and I'm like, okay, I don't understand anything anymore. He's too smart for me.
Yeah, that's what it is. Essentially, these people have distanced themselves from from the public. They're not talking to the public. The public asks questions like, how does a magnet work? Why does the pin fall to the ground? And they say, well, I work with muons or with protons, or he works with stuff that you can't even mention and you never even heard of, and say, I'm so far away.
Didn't you yourself say that they were admitting that it's the end of science or end of physics because they themselves kind of noticed, okay, we're just naming things at this point. How many interactions or events do we have to name and categorize until we're satisfied, and then what do we move on to?
Yeah, but see, the issue is that they had to, for example, they don't have answers to many questions, and we're not talking about physics here. We're talking about math. They can't unify relativity with quantum. So they created a new branch called string theory, which supposedly unifies relativity field equations with quantum field equations. They kind of merge them.
But I thought that was already dead in the water. Like, they don't look at that one anymore.
Oh, they obviously, there's a whole bunch of mathematicians out there just doing numbers and equations in string theory, and they've gone on a tangent, where they've lost track of even the particle physicists, because the quantum guys say those guys are doing stuff. They don't talk to each other either. They don't go to the same meetings. The string theorists go to these conferences. These guys go to this other one. And these guys, the particle physicists, mathematicians, they go to CERN and they smash particles. And the other guys, they don't even go there. They don't do any lab work. They just go into their blackboards and they do equations. And so these guys have developed equations that have nothing to do with what these other guys are doing. And these guys, they just badmouth each other because they say, we don't understand what these string theorists are doing. And the string theorists are saying, you guys are old-fashioned. You're still in the 20th century. You're dealing with particles. We're already working with brains and with lines. They don't work with points anymore. Now they've got these lines. They've got these strings, one-dimensional strings. That's what they work with, not with zero-dimensional particles. That's old-fashioned. And so this is the world these guys are working with. And once you understand that, you know that the world has gone crazy because all these guys are doing is just creating categories here. And here are, those were the quasis. Here we're not finished. We have other categories. We got color, We got color, and let me put this one up there right next to it. We got color. And
is this all going to be on the test?
This is all going to be on the test.
I really feel bad for the people who go to the college and university to study this, though, because they have to actually memorize all this.
Yeah, it's getting to be an encyclopedia of particles.
Forget about making sense of it. They just have to memorize it and spit it right back out on the test page.
Yeah, and then they have to tell you who are asking them a question. All they do is just repeat it like a robot. And here's the color charge. It's a property of quarks and gluons, only quarks and gluons, that is related to the particle's strong interaction in the theory of quantum chromodynamics. Chromo meaning color.
So we have quarks and gluons, which are what a proton
or a neutron have
is
inside.
Made of. So a neutron or proton. Let's just take the proton. We have a proton. Protons are made of 3 quarks.
Yeah.
The quarks, between the quarks, what holds them together, and so they're
marbles
flying out. The marbles, the infinite amount of marbles between them,
called gluons. Right.
And the color charge
is a property.
Is a property
of the strong interaction. It's a property that concerns only gluons and quarks, so only those have color.
I thought the gluons were the ones that did the strong interaction because the strong interaction was the pull one within.
Yeah, but remember we saw a couple days ago where the gluon touches the quark and changes its color from green to red and red to blue.
What was that?
It changes the color.
But not actually the color.
No, it's a property of charge. It's a different kind of charge. We don't have the regular.
Do I even want to know what a charge is?
No, well, we have the regular charge that we did that I explained the other day with the oil drop experiment. That's that's not almost 19th century. That's 100 years ago. That's early 20th century. Now they created 3 kinds of charges. And so not only do we have the standard charge 1.6 times 10 to the 19 coulombs, which is the charge that we had that we inherited from the 20th century.
Old-fashioned.
Yeah, this is old-fashioned stuff. You don't do that. We do that in high school and kindergarten stuff. Now we do the 3 charges that they create, which are the color charges. And it says here, particles have corresponding antiparticle. So we have the particle and the antiparticle. A particle with red, green, or blue charge has a corresponding antiparticle in which the color charge must be the anticolor of red, green, and blue, respectively, for the color charge to be conserved in particle-antiparticle creation and annihilation. They are creating particles out of nothing. They are annihilating particles. In other words, when you don't need the particle because your equation doesn't have a need for it, you bring in the antiparticle, you annihilate it and get rid of it.
That's what I was saying earlier.
Whenever
one's kind of like a thorn in your side, you make the anti that.
Right, because you got to get rid of the particle. And so particle physicists call these anti-red, anti-green, and anti-blue. Okay, all 3 colors mixed together, or any of these colors and its complement or negative is colorless or white and has a net color charge of 0.
I like colorless or white.
I don't know what
those are mutually exclusive. You can't have white and colorless.
Well, yeah. I guess what it is that when you blend these, you get it's like the sun. The sun has all the colors of the rainbow, and then when you put it through a prism, you break it up into all these colors, going from infrared to
but you know what
ultraviolet.
I'm saying. There's a difference between colorless and white. The glass on our window isn't white; it's colorless.
It's transparent. It's translucent. Yeah.
Transparent,
But hold it. But see, again, I think what they have in mind is that sun thing where all the colors are blended and form the white.
That's colorful, if anything.
Yeah, I guess. But that's, I guess, the way they visualize it.
I guess they just mean colorless, like not red, not green, not blue, not anti-red, not green, anti-green, or not anti-blue.
And now we
Either
have,
of those 6.
and to continue here, free particles have a color charge of 0. Baryons are composed of 3 quarks, but the individual quarks can have red, green, or blue charges, or negatives. Mesons are made from a quark and an antiquark. The quark can be any color, and the antiquark will have a negative of that color.
So this color quark is blue, the antiquark is negative blue.
Yeah, correct.
Anti-blue.
Yeah, it's an anti-blue. And this color charge differs from electromagnetic charges. Here's the important part. Since the electromagnetic charges have only one kind of value, positive and negative electrical charges are the same kind of charge as they only differ by the sign.
What does that mean?
Well, they had to. Now we're going to create more than negativity and positivity. We're going to have maybe. Have only one kind of a with charge you only have negative and positive. These guys have more than that.
What guys?
The charges, these color charges. It's not just negative and positive, because you can have an anti-negative, which is not a positive, an anti-positive, which is not a negative, an anti-red, which is the opposite of red, the anti-blue, and so on down the line. And unfortunately, they only deal with 3 colors, but I'm sure the next generation will invent more colors. There's got to be violet, anti-pink.
Discover new colors. Big difference.
Okay.
Right now we're teaching what they teach, but how do they teach it? Because you're teaching it obviously with the tongue-in-cheek, kind of like this is what they say, but how do they say this with a straight face? Like at the university,
they do. They say we've proven it. The guy just accepts it on the basis of authority. He accepts it. He accepts it on the basis of authority.
But how?
It's like religion. You go to the priest and you say, well, I can't read the Bible. I don't know how to read. Dear pastor, please tell me what God meant here. But then the guy says, look, this is the way God said. When you push him too much, he says, only God knows, or God only knows, or no one knows the ways of God, and that's the final answer. This is exactly the same way. They say, look, we've proven it in the lab, and this is the way it is, but that doesn't make sense. Yeah, but we don't understand all of this.
Anti-blue.
Anti-blue, anti-red, anti-green.
I have nightmares of anti-blue. Sounds like a really cool band name.
Yeah, it's going to be the new music. We have the blues and the anti-blues. Okay, so but we're not done. Then now we go into flavor.
Oh, I thought it was gonna be like quasi-colors.
No. Now we get into. See, we have the colors. We have the taste. This is the taste part. Now we get to taste it. Okay, and this is the flavor. It refers to the species of an elementary particle, which is obviously not an elementary particle. They just call it an elementary or fundamental particle, but they're still trying to crack it to see what it's made out of, right? So they're not convinced that it's elementary, but they call it's tentatively elementary. The standard model counts 6 flavors of quarks and 6 flavors of leptons.
Salty, sweet, bitter.
More or less sugary. They are conventionally parameterized with flavor quantum numbers. These are numbers, these are equations, these are values that they assign these things that are assigned to all subatomic particles. They can also be described by some of the family symmetries proposed for the quark-lepton generations. And we have generations of generations.
Wait, so what's the flavor? I still don't understand.
No, we don't know. Nobody knows. Particle man. What is it?
Something.
Nobody. What's it like? Nobody knows. Nobody cares. Nobody knows. Nobody cares. It's this is.
No,
does this make any sense? Does any of this? It's not important. Man. Yeah. What's it like? It's not important. Nobody knows. And I say nobody cares. Yeah, nobody cares. Nobody asked the right question. What are you doing in that lab? Well, I'm doing math. I'm doing equations. And I'm looking at all these. You can say they're looking at these pictures, these images, and they say, oh, I got to find a name for this guy. It's got a different mass, a different behavior than this other guy. And then the next time you smash him, maybe it makes a different curve. They say, oh, I found a different particle here. I'll call this one Johnny. And you get a Nobel, and say because you discovered a new squiggly line there. I mean, what does any of this have to do with science anymore, with physics? They've gotten so far off, and they still can't explain this. They can't explain. Too bad. This is how simple this system is. I mean, look how simple it is. Two pieces of metal, and they can't explain, but they can explain to you or describe mathematically. They can tell you, about flavors of quarks, of gluons. They can tell you all this subatomic stuff, which they've never seen, by the way, which is kind of weird because you would think that, those pictures that I just showed you about the squiggly line, you would think you would see some kind of little ball in there. At some point, at the end of the rainbow, there's got to be a pot of gold, right? And so if this squiggly line makes like a circle, we'll just look into that circle and find out what what that particle looks like. Or even better yet, if you can see that squiggly line, right? Let's assume that line is real. This is my argument against quantum mechanics, against those traces. They say these are traces. Fine. Okay, there are traces. What makes a trace? Footprints. You get a bear. True. And a bear steps on the snow, right? A polar bear, maybe. He steps on the snow and you follow the trace. You say, okay, a bear walked through here. But then you can measure the size of the footprint and say, okay, this one measures 1 foot long and half a feet wide, right? Whatever. Okay, so you can measure the size of the foot. You can infer the size of the foot by the footprint it made. Here they have all these footprints, these traces, which they took a picture of. Supposedly, I guess that's what they're telling you, right? That's what that picture shows. All you have to do is take your ruler, just make that very big, take your ruler and measure across the line and say, this was made by a particle that is so wide.
Isn't that what they've done?
No, they don't worry about measuring. What they do is talk about mass, energy, speed. They don't talk about size.
What?
No, they don't talk about the size. Here's the particle. Okay.
I like the big red ball.
Yeah, big red ball. This is a quark that's been hit by a gluon and turned red.
It's
okay?
a red.
It's a red.
Red or anti-red?
This could be the anti-red for all I know. I don't know. Maybe I don't know. Here's a particle. Okay, it moves. It creates a line. It creates a swath. In the chamber, inside the chamber, right? So just measure the diameter of the line that it made, and that should give you or measure across the line. That should give you the diameter of the ball. That's how simple it is. Not only that, if you do it many times, then you can get a picture or an image of what the particle looks like. They've never seen any of these. They talk about gluons. Gluon is smaller than a quark, which is smaller than a neutron, which is smaller than an atom. They can't tell you what an atom looks like, but they're dealing at the gluon level inside the image gluons. And they say, well, we don't know what a gluon looks like. We don't know what an atom looks like. Forget about a gluon. But they can see the traces of these things. What sense does that make? The analogy I use is the following. Here you have the carpenter and the mason. They come to your house, they build your house.
Mason or the mason?
This is the mason. And they come to your house and they build your house. And you say, okay, do you know what a nail looks like? Of course. Nail looks like this, and that's what I use to hammer each board that makes the walls of your house. So what does my house look like? Oh, I don't know. I can't tell you what your house looks like. But I can tell you, but because I deal with at the nail level. I hammer nails here. I hammer the boards, put them all together, build the wall. And from the wall, the roof and so on, and I build your house. But I don't know what your house looks like. I can't draw for you your house. That's what these people are saying. They're saying, look, we deal with gluons. We can see those on the screen. We don't know what they look like, but we see their traces. And you're talking about gluon. You're talking about the extreme of bigness. It's the smallest thing you can imagine, almost, a gluon. It works between quarks, which are giants in comparison to the gluons. And of course, the quark is a tiny little, Lilliputian compared to the neutron, which is, it's a 10,000th of the atom. A 10,000, because the atom extends all the way to the electron. And the electron is orbiting, way in left field over there. And so you got the big house. The big house, you don't know what the house looks like, but they're dealing at the gluon level. You tell me, at the nail level.
But then what are these traces that they're seeing?
That's a good question. I'm saying these are not traces because, first of all, if they're going to take pictures of traces, they're taking pictures of movies. And you're going to say, well, how did you take a picture of this whole squiggly? Was the camera, I guess they have the camera open for, how fast is that? It's got to be really fast. Here's an explosion. Wham! And we're talking about the atomic level. It's got to be almost at the speed of light. And they claim they have shutters that can image that whole thing doing a curly-Q.
But that's how that works.
In a millionth of a second or whatever.
That's how it works. The faster it is, the blurrier. If you take a picture out of the window of a moving train, you get a blur.
Yeah, a blur. Yeah, but these guys aren't getting blurs. These guys are getting but the trace, like you said, it's a blur. And even conceding it's a blur, it's a trace, whatever, footprints. Yeah. We should be able to measure across that blur and say, well, how big was the particle that made this?
That's a different issue. I'm saying
yeah,
you would expect to see traces if it were a particle because it's going so fast. It's going so fast it's impossible to have a camera that's so fast that it takes
but this is my point. My point is that if the camera is open for that millionth of a second, and during that millionth of a second, this guy, makes a trace. Does that particle have a chance? Does the shutter have the speed and all that calibrated to the point where this guy does a curly-Q, because some of these, go around a couple times. And just try to do it with a normal camera, just see what you can take a picture of and, get that shutter open and let someone do, some kind of weird thing where you have a curly-Q. Is the camera able to get all that whole roll around?
Yeah. They have cameras that point,
I guess they do.
They have cameras that point to the sky and they're so slow that it basically blurs all the stars. It shows the trace of the stars, essentially. But that's really just technical things that we're talking about.
Yeah, but in this case, since it's not a direct image, it's computer generated. I have more problems here because
the opposite would be impossible. It'd be impossible to get a picture of just the particle.
Correct, I agree there.
No,
I agree there. But what I'm saying, I also have problems with the whole curly-Q thing. This guy goes two or three times around. This guy is able to trace that whole thing. That's the first problem I have. But let's concede that. Let's assume they have the shutter open for that billionth of a second or whatever. But then you have the issue of, this is not done with a camera. Okay, that's important. It's done with computers. It's computer generated.
Well,
it's done with many sensors.
But sensors.
Yeah.
There's a couple steps between sensors, computers, and what they
But
see.
the algorithms in there are already designed to treat every little blip as a particle. All these quasi-particles become particles, or all these wave functions become particles. So we've got verbs. We're filming verbs. And they're not even filming, and they're not particles. There's nothing underlying the verb. There's no kangaroo jumping. It's just jumping. And that makes you kind of think they're taking pictures or imaging jumping. Great. And they're saying, we're going to call that jump Johnny, and the hop is Joey, and then we'll divide that into hopscotch.
Actually, going back to what you criticized earlier about there having to be a dot at the end, wouldn't you not see a dot at the end because the size of the particle stays the same? So you would have a line. You wouldn't have a line and a dot at the end because it is the same width.
Yeah,
as the whole
except
line.
we got a problem there as well. And the problem is that they say that all these things annihilate, they decay at the end of the rainbow. There is no pot of gold.
Well, yeah,
It's just
that's
when
to
you
be
end
expected.
at the end of the rainbow, there's just rainbow.
But that's because that's what they see. They don't, or whatever the detection detects is it doesn't have a line that just goes at infinitum. It's just it's like a scrape. It's like a beginning and an end.
Right, you would think there's, I mean, does this thing have enough time because this is done very fast.
No, but you're not getting it. The slower the camera, the more trace you have. It's the opposite.
I don't know.
But that's not my point. My point is the decay. That's kind of what you would expect, a beginning and an end if it decays. If it didn't decay, if these particles didn't decay, then you'd have the line
like those
going
skyrockets. A skyrocket goes and then blows up, and you can't say let's look at the skyrocket in the air. No, it's not there anymore. It blew up. It disintegrated.
But that's what these traces.
You can find it in the morning. When the guy sweeps and you find all the.
That's what these traces signify or indicate that it has a beginning and an end. At each one of these particles, because if the particle didn't have an end, then it would just keep going. You'd have the traces. You wouldn't see the line. You'd just see the beginning, and then it just goes off the screen, each and every one.
Anyways, that's the particle zoo.
No,
quite
that's
a
the
zoo.
Quasi-Particle zoo, which is even weirder.
And all the flavors and
colors.
colors and all these properties that all these non-particle,
And
all these verbs have.
And we're none the wiser. That's
And we're
the
none
point.
the wise. No, but they hold expectations. They have these expectations that all this will create some breathtaking technology. And let me just finish with a final word on this. Technology is built on atoms and upwards. You don't build technology on subatomic particles. You can only build starting at atoms. And these people are holding or giving you the misleading impression that by going deeper and deeper to the gluon level, they can come up with some technology where they can build things with gluons or whatever. They can handle, with their tweezers, some high-level tweezer, they can start pulling gluons and do something with just gluons, for example. That's what they're, giving you the misleading impression of. They're creating false expectations. And so the military, all these people, they like all this stuff because they say, maybe these guys can come up with some kind of new weapon we can use against, the Russians, or the Russians against the Americans, or the Americans against the Chinese. And this is the issue. The issue is that, this is misleading. We're done with that part of, of science called particle physics. And it is at the end of physics in that sense that they don't know what to do. They just create more particles and more things to do, so that they create new jobs for the new generations. And all they're doing is just a bunch of math. And the math is not meaningful anymore, even for a lot of them. And those people who are mathematically inclined, that go to the university just to study specifically the mathematical physics, some of them get bored and they quit because they say this is all nonsense. And the ones who continue are the ones they say, hey, I can still make a buck with this. And that's about all we have today. We'll see you tomorrow, same time, same station. We'll see you then. Don't forget to watch Real Physics. Don't forget to go to Buenos Aires to the conference. We'll see you then.